Welcome to this explainer. Today we are taking a seriously detailed 4-month scientific proposal and turning it into a story of creation, destruction, and a literal trial by fire. We are looking right at the bleeding edge of structural engineering. We're going to explore exactly how a team of researchers plans to take sustainable 3D-printed concrete, intentionally break it, heal it using fibers spun from volcanic rock, and then shove the whole thing into a blistering furnace. It's an absolutely incredible look at how science works to ensure that the sustainable buildings of the future aren't just green, but literally built to survive an inferno. To wrap our heads around this monumental effort, we're going to follow a really clear chronological roadmap today. We'll start with the future of concrete, move into designing the mixes, cover the print, break, and repair process, jump into the actual trial by fire, and wrap it all up with the timeline and takeaways. All right, let's kick things off with Section 1, the future of concrete. So, here is the multi-million-dollar question driving this whole thing. Can sustainable 3D-printed buildings actually survive a massive fire? I mean, we all know the construction industry is desperate to revolutionize how we build, right? 3D printing is amazing because it saves time, it cuts down on intense physical labor, and it slashes material waste. Plus, we want to use sustainable materials to do it. But before we can actually start living and working inside these futuristic, eco-friendly structures, we absolutely have to know they're safe. Fire safety is non-negotiable. If these new green materials can't take the heat, we simply cannot use them. Think about traditional concrete for a second. It relies heavily on ordinary Portland cement, or OPC, which, let's be honest, comes with a massive carbon footprint. To combat that, researchers are proposing these brilliant, sustainable eco-mixes, where 30 to 50% of that carbon-heavy cement is completely replaced by industrial byproducts. Stuff like fly ash, slag, or geopolymer binders. They might even throw in some recycled aggregates. It is fantastic for the environment, but it creates one huge glaring variable. These new mixes have totally unknown fire risks compared to the tried-and-true traditional stuff. Moving right along to Section 2, designing the mixes. To pull this off and reinforce this new concrete, the researchers are bringing in a fascinating healer material. It's called BFRP, or Basalt Fiber Reinforced Polymer. Now, normally when concrete structures crack and need to be strengthened, engineers will use glass or carbon fibers. But here, the researchers deliberately chose basalt, which is literally spun from volcanic rock. And why would they do that? Because basalt offers way higher thermal stability. The research shows it maintains its structural integrity up to a staggering 800 degrees Celsius, and it's totally inert to alkalis. It is basically the ultimate high-temperature armor. To actually test this out, the battle plan relies on a highly specific matrix of concrete beams, each one measuring 300 by 100 by 100 millimeters. They're testing 4 distinct groups to cover all their bases. Groups A and C act as the baselines. That's traditional concrete versus the new eco-mix, both left totally unrepaired. Then groups B and D represent those exact same mixes, but this time they're repaired with our basalt fiber armor. This controlled 4-way setup is exactly how they isolate how well the sustainable mix performs, and exactly how much that volcanic rock fiber actually helps. Which brings us to Section 3, print, break, and repair. Here's the thing, you can't really test a repair if there's nothing broken to begin with. So before a single flame is lit, the lab researchers are going to intentionally damage these beautifully printed concrete beams. They're going to load them quasi-statically into a machine that applies a 3-point bend right in the center. And they'll push down just hard enough to create a perfectly controlled flexural crack that is exactly 0.3 millimeters wide at the midspan. This is super important because it perfectly mimics the kind of real-world structural failure and cracking that real buildings experience over time. Now for the crucial part, healing the wounds. And they aren't just slapping some duct tape on it. They follow a super strict, internationally recognized protocol from the ACI 440.2R guidelines. First up is surface prep. They grind the concrete down to a really specific roughness profile called ICRI CSP3, just to ensure there is zero dust or oil. Next is the bonding phase, applying a saturating epoxy resin and laying down 2 unidirectional layers of that dry basalt fabric. Finally, the curing phase. The epoxy needs 48 full hours to harden, and they actually use a gentle heat of about 40 to 50 degrees Celsius to accelerate it, which actually improves its performance at high temperatures later on. Okay, so we've printed them, we broke them, and we meticulously healed them. Now for Section 4, the trial by fire. 980 degrees Celsius. That is the number that matters here. The beams are going to be thrust into a specialized furnace, following the extremely severe ASTM E119 standard fire curve. Now, this is not some slow, gentle warming process. This is an aggressively rapid heat-up designed to simulate a major, raging structural fire. It ramps up to roughly 538 degrees in just the first 30 minutes and hits a blistering 980 degrees Celsius by the 90-minute mark. So how do we actually know when a beam has officially failed? Well, the research team is going to watch like hawks for a few specific failure criteria defined by the standard, pushing these specimens for up to 2 agonizing hours. First, failure happens if the beam bends or deflects by 10 millimeters. It also fails if the temperature on the unexposed side of the beam rises 140 degrees Celsius above room temperature. That's a huge one, because in a real building, if the back of a wall gets that hot, it can instantly ignite whatever is in the next room. And of course, total structural collapse or direct flame penetration means the test is immediately over. And to make absolutely sure not a single piece of data escapes those flames, the specimens are going to be heavily instrumented. You can't just stare at a fire and know what's happening inside a rock, right? So they literally wire the concrete with 8 K-type thermocouples per test. Some go internally at mid-depth, some on the unexposed back face, and some right on the surface directly facing the fire. They're also using LVDT displacement transducers. These are highly sensitive devices that track the physical bending of the beam in real time, meaning they can detect a loss of structural integrity long before the whole thing totally collapses.
Let's bring it all together with our final section, timeline and takeaways.
The actual day-by-day project schedule reveals a massive, perfectly orchestrated sprint. We're talking about 2 researchers on site handling all the mixing, the heavy lifting, the dangerous epoxies, and the intense heat of the furnace. Meanwhile, a 3rd external support person coordinates the materials and crunches the flood of incoming data. Literally every single day of this intense 4-month schedule is mapped out. Across these 4 months, the momentum is just unstoppable. Month 1 is entirely consumed by finalizing those tricky mix designs and gathering the materials. Month 2 is fully dedicated to the super delicate process of 3D printing and curing the concrete. Month 3 brings the intentional damage and the really meticulous application of that basalt armor. And finally, month 4 leads straight into those blistering furnace tests and the deep data analysis. All of this extreme testing culminates in some absolutely vital deliverables. The output here isn't just a basic pass or fail. The team is going to produce highly detailed time-temperature curves and deflection charts that show exactly how the beams behaved second by second while inside the fire. They're even going to take core samples of the burnt concrete to test its post-fire residual compressive strength, just to see what is actually left. They'll document the spalling, which is when the concrete surface violently chips and flakes away in the heat, and they'll analyze the charring of the basalt fiber. This data is the proof. It will definitively show if sustainable mixes fortified with basalt can truly withstand an inferno. Because the ultimate goal of this entire 4-month endeavor isn't just to play with fire for fun. By analyzing the results and assessing exactly how well this basalt fiber repair holds up, the researchers hope to propose improved protocols that could literally rewrite the safety codes for how we construct and repair our modern habitats. And that is really what this is all about. I'm going to leave you with this final thought. If we can definitively prove that recycled waste, industrial byproducts, and fibers spun from volcanic rock can survive a 980-degree trial by fire, what limits are left for the sustainable cities of the future? When we combine cutting-edge 3D printing with extreme material resilience, we aren't just changing how we build. We are ensuring that the eco-friendly skylines of tomorrow are built to last. Thank you so much for joining me for this explainer, and keep exploring.